Hey, welcome back to part 2 of our day 1 directional derivatives lesson. So let's take a look at another example. We want to find the directional derivative of the following function, e to the xy plus y, at the point 2, 0 in our direction negative 1, I plus root 3, j. Now, remember what we're saying here. We're on some sort of surface right here. If we imagine this as being our surface, we're at the point 2, 0, and we're heading left 1 up root 3. So we're heading in this direction right here, and we want to find out what is the rate of change along that surface at that exact point. So we're basically finding the slope at a point in a certain direction. To do this, remember a couple things. One, we will be needing our partials. Remember, that's what our rule up here says to do. We do need our partials up here, fx, fy. So let's go ahead and find them. Fx, the partial with respect to x, is just going to be e to the xy. Don't forget chain rule. The derivative of xy with respect to x is just y. And then we need the partial with respect to y, which is again e to the xy times x this time plus 1. And then we're going to find our slope at these 2 points right here. So if we find the slope at the point 2, 0 for fx, ready? We would get, if I plug in 2, 0, we would just get e to the 0 times 0, which is just 0. And same thing for the y. We would just get e to the 0 times 2 plus 1. So we would get 2 plus 1, which is 3. And again, from here, I can kind of get my diagram. And now, next, we're going to find our duff, but you got to be really careful. One thing we talked about is this has to be a unit vector. This is not a unit vector. So I need to make it a unit vector. So u will just be, and you can kind of write this in chevron form, negative 1 root 3, and I'm going to divide that by the magnitude. This becomes 1 plus 3, so we get negative 1/2 root 3 over 2. And of course this can give us our direction too. We would get our direction from here. So in order to calculate our directional derivative now, should put a little hat there. This is going to be our partial. Let's look at our rule up here. Our rule says when they are partial with respect to x, which we said was 0, times, well, there's my cosine, and there's my sine of theta, times negative 1/2, plus the partial with respect to y, which we said was 3, and we're going to multiply that by the sine of theta, which is root 3 over 2, and we just get 3 root 3 over 2. Remember what this is? This is the change in the z-coordinate. In other words, it's the steepness at that point. It's that steepness at the point that we're looking at right there. All right, so very easy to do. So let's take a look at another example. Then we'll see, maybe you might recognize kind of maybe a shortcut here. So we'll see about that if we can. Okay. We can also write the equation of a directional vector derivative if we are not given a point. Now remember, this is going to be more of a generic one. This is more like a derivative itself. If we're not given a point, where this is a slope itself, the slope itself, if I'm not given a point, this acts more like a derivative, a true derivative right here. So I can find the steepness at any point. So write the directional derivative for the following surface and vector. So here's our direction that we're heading. And we have to find our partials, of course. The partial with respect to x becomes y squared minus 4. The partial with respect to y is 2xy plus 3. Now, be careful. Again, this is not not a unit vector. And because it's not a unit vector, we have to make it one. So u is, ready, 3, -4. And of course, this is just a 3, 4, 5 triangle, so I can just put those over 5. Right there. There's my cosine. There's our sine of theta. So therefore, our directional derivative then would be the partial with respect to x, parentheses, y squared minus 4 times 3/5. Be careful, I'm going to subtract out that negative right there, so I'll make this a minus the partial with respect to y, 2xy plus 3, and multiply that by 4 at the 4/5. Now, let's see if we see something right here. Notice, this is my partial with respect to x. This is the rate of, this is the change in the direction of x, dx. Plus, again, don't worry about the minus, let's just get back to that. This is my partial with respect to y, and this is my change in y's. How y is changing. Cosine of theta, sine of theta, sine of theta, cosine of theta. So it's my change in y's. And if you kind of notice, this looks very much similar to a dot product. And the dot product would be this, fx, fy, dot that with dx, dy. Well, of course, we're dx and dy, this is my cosine theta, and this is my sine theta. So let's take a look at an example where we can use our dot product. Finally, we can simplify the directional derivative into a dot product. And we can, so let's take a look at this last example right here. Take the given function and direction vector and convert to a directional derivative into a dot product. So here's our function and there's our direction. So it's just like the last one we did. So if I were to rewrite this, write the appropriate notation, we would say the directional vector, the direction vector, whoops. There we go. Go back to black here. That our direction vector, or Duffman, would be the partial with respect to x, the partial with respect to y, dotted with this -1 root 3. Again, there's my cosine theta, there's my sine theta. And remember though, this must be a unit vector, right? But right now it's not a unit vector. So I'm going to have to divide both of these by 2. We know by 2 because we saw this in the first one over here. That was up here, right? Up over here. That was our direction vector. It does have to be a unit vector still, so don't forget to divide them by the 2's right there. So this is another way we could write our direction vector. So let's take a break right now. Let's go to part 3, and we'll take a look at the last few examples.